Hello, this is Mr. Henry, and welcome to lesson 1.4. In this lesson, we're starting to talk about square roots and cube roots. The essential question says, how do I use square roots and cube roots to solve problems? In the warm-up, I have you try to explain why the solution of the following equation is m equals 3. So I have this equation 5 times m to the third power equals 135. So why would m equal 3 in this problem? Well, if you remember a little bit about solving equations, probably the first thing most of you might have tried is divide both sides by 5. Okay, so you get m cubed equals, let's see, 135 divided by 5 equals 27. So why is m cubed equal to 27? How do we know that m is 3? Well, m cubed means m times m times m. And what number times by itself 3 times gives us 27? The answer is 3. 3 times 3 times 3 is 27. So that fits the puzzle. 3 is the number you'd plug in here that would make this true. And these square roots and cube roots that we're using in this lesson are the start of something big. They're going to be used a lot, especially in the next module when we start talking about the Pythagorean theorem. They're used in every single Pythagorean theorem problem. Okay, so let's see here. Square roots. The square root of a number is the inverse operation of squaring a number. Every operation in math has an opposite. So the opposite of addition is subtraction. The opposite of multiply is divide. The opposite of squaring something, like a squared, is the square root of that thing. So a squared square rooted cancels out the square. And the same thing for cube root. Cube root is the inverse operation of cubing a number. And a cube, for those who don't know, that's to the third power. So, like a cubed, 5 cubed, 2 cubed. Squaring, as you saw down here, is when you take the number to the second power. B squared, C squared, 2 squared. Now, to do these problems throughout this lesson, it might be helpful if you have a nice handy little chart of some of the perfect squares and perfect cubes. So let's do that. So I have here numbers listed 1 through 12. You also have them on your note sheet. So let's start with perfect squares. So 1 squared is 1. 2 squared, which means 2 times 2, is 4. 3 squared is 9. 4 squared, 16. Hopefully you're seeing the pattern. 5 times 5 is 25. And 36, 49, 64, 81, 100, 121, 144. All right. Perfect cubes is when you take the original number and you take it times by itself 3 times. So this is going to be 1 times 1 times 1. 2 times 2 times 2. 3 times 3 times 3. 4 times 4 times 4. 5 times 5 times 5. 6 times 6 times 6, which I don't know off the top of my head. Do 6 times 6 times 6. 216. And 7 times 7 times 7. 343. 8 times 8 times 8. 512. Times 9 times 9. 729. By the way, since I'm starting to type this stuff out and it's just monotonous, there is one of the standards that say that you should be able to recognize by sight some of these basic perfect squares and perfect cubes. You should know what they are just by looking at them. So if I gave you the number, for example, 144, you should be able to look at that and go, oh, yeah, that's a perfect cube because that's 12 times 12. And as far as or perfect square, as far as the perfect cubes go, I don't know how high they would expect you to memorize. I got up to about 5. I don't know anything higher than that, and I don't think you would need to either. So probably 1, 8, 27, 64, maybe 125 is probably all you'd need. But here's a list at least so that throughout the lesson we can periodically look back. If we get a number and go, oh, I think that's a perfect square, we can look up the top of our page and go, oh yeah, there it is. But you should definitely know all the perfect squares up to 12. Perfect cubes maybe up to 4 or 5. So let's do this. Solve an equation using square roots. So here we have our first problem, problem A here. We have x squared equals 16. So if we would square root each side, if I would square root x squared, it gives me x. Because square rooting and squaring are opposites. It's almost if I said I have x plus 2 and I minus 2. The plus 2 and minus 2 cancel out, and I'm left with just x. And on this side, if I square root 16, we can look back to the chart if we need to. The square root of 16 is 4, because 4 times 4 is 16. Letter B. 3m squared equals 27. Now, before we can do the square root and get rid of this m squared, we have to get rid of this 3 out front. We want the m squared piece by itself first. So the way we get rid of a multiply by 3 is we divide by 3. So m squared equals 9. And now, when you square root on both sides, the square root and the square cancel, so m equals. And the square root of 9 is 3, because 3 times 3 is 9. You check back to your chart if you need to. Square root of 9 is 3. Now, in letter C here, we have a fraction. It says y squared equals 4 over 9. Well, if we square root it, which is what we should do to get the y by itself, well, kind of what we do here is we separate it into 2 separate problems. We think about the square root of the top and the square root of the bottom. And I can do that. I mean, the square root of the top is 2. The square root of the bottom is 3. So y equals 2/3. I square rooted the top and the bottom separately, just as part of the fraction. Letter D's just like letter B. So I'm going to divide by 9 on both sides, and I don't know what that is off the top of my head. 225 divided by 9 equals 25. But I do know off the top of my head, if I square root both sides, the square root of 25 is 5. So J equals 5. So now I would like you to try some problems on your own. Here's letters E, F, G, H. Please pause the video. Try them on your own. When you're ready to continue, hit play, and we'll go through them together. Alrighty, I'm going to fly through these guys since you should have already done them already. So we start by divide by 4 on both sides. X squared equals 9. Square root, x equals 3. I'll switch colors. Square root both sides, giving you r equals the square root of the top and the square root of the bottom. That's 8, that's 4, that's 2, so r equals 2. Square root each side gives you p equals 10. Simple, simple, simple. Ooh, ain't he fun? I remember this stuff. So you gotta subtract 4 on both sides to get rid of the add and subtract first. That gives you 72. Divide both sides by 2, giving you g squared equals 36, I think. 72 divided by 36. (72) divide 2 equals, yes, 36. And then we square root each side, cancels out the square, and g equals 6. Well, that was fun. So square roots are used in quite a few places, and actually you're going to see the higher you get in math, if you get beyond Algebra 1, exponents get used more and more and more often. They're used a lot in Algebra 2, they're used a lot when you get into geometry, they're used a ton when you get into things like calculus, talking about functions, which we'll be doing later this year. They're used quite a bit. These next 4 problems, this next example, is now we're looking at cube roots. So when you're doing a cube root, it looks kind of the same, except in here, in this little space here, you actually put a little 3 to show you're doing a cube root. And a cube root cancels out a cube, so y equals. And the cube root of 27, if we flip back to our chart, perfect cubes, 27, the cube root is 9. Cube root is 9. Letter B, we're going to take the cube root of t cubed and the cube root of 1/8. So the cube root and the cube cancel, giving us t equals. And on the other side, we're going to separate it just like we did with the square root. The cube root of 8. And the cube root of 1 is still 1, because 1 times 1 times 1 is 1. The cube root of 8 is 2. So t equals 1/2. Letter C. Just like before, we have to get this w cubed by itself before we can do a cube root. So we're going to get rid of the 2 by dividing by 2 on both sides. And w cubed equals 8. And if we cube root each side, w equals 2. Because we just did cube root of 8 over here was 2. So cube root of 8 here, still 2. Letter D. Let's see. Well, we've got to get rid of this. We've got to get this piece by itself. So we're going to get rid of this minus 6. We're going to add 6 to both sides, giving us a cubed equals 1. And the cubed root, I don't write my cube roots very pretty. My cube root of 1 is 1. So it's pretty much the same procedure with square roots and cube roots. So go ahead and try these out. Pause the video, go through them together, or by yourself. When you're ready to continue, hit play. Then we'll go through them together. Okay, let's see here. Jump to red. So if I cube root each side, the cube and the cube root cancel, giving me c equals, and the cube root of 216 is 6. I remember us doing that up here. There it is. 4b cubed. So I gotta get rid of that 4. Give me b cubed equals 500 divided by 4. Clear. 500 divided by 4 equals 125. Divide both sides. Oh, not divide. What am I doing? Cube root each side. And those cancel out. We get b equals 5. Cube root, cube root, cube root. So we got k over here, and on this side we have to break it down into the top and the bottom. And let's see, k equals, the top gives me 8. No. Cube root of 64 is 4. And 216 is 6. And 4 over 6 simplifies to 2/3. And letter H, let's see, minus 4 minus 4, 3h cubed equals 81. Divide both sides by 3. H cubed equals 27. Cube root that beast. And that one. And h equals 3. So I would say so far not too bad. Not too shabby. Pretty easy. Let's figure out and do some applications. Let's use them in word problems. Oh, but first, a little summary. What would happen if you take the cube root of a number that is not a perfect cube? Interesting. And compare this result. What would happen if you take the square root of a number that's not a perfect square? So maybe take your calculator and do some square roots and cube roots. And for those folks out there who are curious how to do a cube root using a calculator like this, we're going to take 27 to the power of, we'd have to do 1/3 as our power. And my calculator doesn't give an answer. Your calculator should. The cube root of 27 is 3. But to do a cube root, for example, using a calculator like this, square root, you use the 1/2 power. That means square root. And a cube root, use the 1/3 power. Just so you can try it out on your calculator to see how it works, if it works. That's how you would do it. So go ahead and try that right now. Okay, so what did you find when you did your square roots and cube roots of different numbers and you tried it out? Probably what you found is that if you took a cube root of a number that's not a perfect cube, you probably got some big, ugly, long, ugly decimal. Just like happened when you took the square root of not a perfect square. You get these irrational numbers that we talked about in the first 2 lessons of this chapter. So you get some big, ugly number. And just to show you something I got here quick, this website called Wolfram Alpha, it's basically a website that does a whole bunch of awesome like mathematical stuff. It can answer lots of science questions. So I popped in here 8 to the power of 1/3. like I asked you to do in class, or on the video before I canceled it, before I paused it, and it gave me the answer of 2, just like we said it should. I mean, that's how you do the cube root. But if you type in some number that's not a perfect cube, say, for example, 10, gives me, holy cow, that's a big, long, ugly number. So you get these huge, ugly, ugly, ugly numbers if you're taking cube roots of numbers that are not perfect cubes. So you get your irrational numbers again. The only difference that you might notice is that if you tried to take the square root of a negative number, you get an error. You can't do it. It's impossible. But if you take the cube root of a negative number, it does work. Let's see if Mr. Wolfram Alpha can do this for us. If we take the cube root of -8, it gives us an answer of -2. But if you take the square root of a negative number, like -4, it gives us an answer of -2. That's not true. You can't take the square root of a negative number. It lies. Apparently it's not a very good website. It's not very smart. But it can't be done. You get a number that doesn't exist. You cannot take the square root of a negative number because, Mr. Wolfram Alpha, if you take -2 times by -2, that's not a 2. If you take -2 times by -2, you do not get -4. It's impossible. There's no two numbers you can multiply together to get a negative number. And I think we talked about this earlier in the lesson, or earlier in this chapter. You cannot take the square root of a negative. It does not exist. So, those are some differences and some similarities. If you take square roots and cube roots of numbers that are not perfect squares or perfect cubes, you get irrational numbers. But with cube roots, you are allowed to take the cube root of a negative number, but you're not allowed to take the cube root of you're not allowed to take the square root of a negative number. Now we're ready for application. So here we go. It says the volume of a cube can be found using the formula V equals S cubed, where S is the length of the side. Okie dokie, cube it is. Length of the side is S. Alright. If the volume of the cube is 343, what is the length of one side of the cube? Well, let's see. If I plug it into my formula here, the volume is 343. And they're asking us what is the length of one side, which is the S. Well, to find this S, just like we did in the problems up here, you take the cube root of the thing. So I'm going to cube root each side. And a little 3 in there. And if I take the cube root, it cancels out the cube. So I get S equals, and 343. Was that one of our special cube roots? There it is. 343 is the perfect cube of 7. So if I take the cube root of 343, I get 7 yards. So each side of the cube is 7 yards long. Letter B. It says Sam and Allison are trying to find the side length of a square with an area of 100 centimeters squared. Of a square. So we have a square. They're trying to find the side length with an area of 100 centimeters squared. Okay. So this is what they're talking about. Sam's method is to take the area and divide by 4 to get a side length of 25. Okay, so he took 100 divided by 4, which does equal 25. And he thinks that's how big each side is. So he thinks each side here is a 25, 25, 25, 25 square. That's not a square, but play pretend. Use your imagination. Allison's method is to take the area and square root it. Yeah, checks out, and you get a side length of 10. Okay, so she thinks it's 10, 10, 10, 10. Determine who has the correct method and explain why the person with the wrong method is wrong. Well, if I would do the problem on my own, let's see. The area is 100. So area for a square, that's the formula for the area of a square. We actually did that, I think, one of the other problems. Nah, but it's similar to the cube. But that is the formula for the area of a square. It tells us that the area is 100, and we're trying to find the side length. Sam divided this by 25. Allison took the square root. Well, if I'm trying to get this s by itself, the opposite of s squared is square root. Allison is correct. I needed to square root each side, so each side would be 10. So why is Sam's method wrong? What does it look like he did? It looks like, instead of Sam thinking about area, to me, it looks like Sam was thinking about perimeter. The perimeter of a shape is when you add up the outside, and if you did what Sam did, and you add up all four sides, that gives you a perimeter of 100 when we wanted an area of 100. So Allison was correct. You would square root it to get rid of the s squared. Sam is wrong because he was thinking about perimeter, not area. Here's one problem I'd like you to try. It says Jacob used the Pythagorean theorem to try to find the length of a missing side of a right triangle. Okay, sweet. His work so far is shown below. And you can see it's the a squared plus b squared equals c squared, which if you don't know, that is the Pythagorean theorem. We'll be using it a lot next module. Finish this problem to find the hypotenuse of the triangle. Alright, so what I'd like you to do is I'd like you to finish this problem. I want you to find out what is the value for c in this problem. Pause the video, do it on your own. When you're ready to continue, hit play, and we'll go through it together. Let's see. Personally, I would do 6 squared is 36. 8 squared is 64 equals c squared. I'd add them guys up. 64 plus 36 gives me 100. And then I would square root each side, and I'd get c equals 10. So the hypotenuse would be 10 units long. One thing I thought of just now that we didn't talk about, I guess it's kind of assumed. When I was talking about cube roots, I had a little 3 in the corner. Like cube root of 27 is 3. But when I have square root, I don't put anything in the corner. You could, just so you're aware, you could write, make it a little bigger. I could put a little 2 here, and it's exactly the same thing. We are just so used to when we use this symbol, using it as a square root symbol, that it's implied, it's understood that there's a little imaginary 2 hiding in there. So if you put down the square root symbol, it means square root, and to do a cube root symbol, then you'd put down a 3. Now, if you're thinking, wait, Mr. Henry, if there's a square root and a cube root, are there such things as like fourth roots and fifth roots? The answer is yeah. If you had, say, b to the fifth power, you could take the fifth root of that and find out what b is. I don't want to do it, but it exists, just so you know. Letter D, last problem for the day. Go ahead and pause the video, do the problem on your own. When you're ready to continue, hit play, and we'll go through it together. Alrighty, it says cube A has a volume of 216 inches cubed. Square B, so we've got cube A and square B. This guy has a volume of 216. This guy has an area of 81. By the way, folks, what you see me doing is exactly how I would do the problems if this is me taking it during a test. I would draw the picture, and I mean, I haven't even read the rest of the problem yet. But this is what I would do to help me understand what the problem is saying later on. So now I have a good visual understanding of what the problem is talking about. Cube A has a volume of that. Square B has a volume of that, just like I've shown. Which shape has the smallest side length? So side length is here and here. I want to know which one has a smaller side. And then it says how much smaller is the smaller side than the bigger side. So for me to answer this question, the thing I've got to figure out is how big are the sides? Because it says which one is bigger, and then how much, or which one is smaller, and then how much smaller is the smaller one than the bigger one. Well, I can't answer that if I don't know how big the sides are. So my goal in this problem is to figure out how big are the sides of each. From past experience, about 3 problems ago, we know that there is a volume formula that looks like this. And there's an area formula for a square that looks like that. If I start plugging in my data, my information, 216 is the volume, s cubed, 81 is the area, s squared, and I solve this, I'm going to find out how big each side is. So for the cube, I need to cube root 6 equals s. For the square, I need to square root s equals 9. So, how big are the sides? This guy, the sides are 6 big, and the square, the sides are 9 big. Question was, which shape has the smallest side length? Well, the answer is the cube. The cube has the smallest side length. Okay, answer number 1, check. Number 2, how much smaller is the smaller side than the bigger side? So we're looking for a difference from one to the other. Well, if you're ever finding a difference, or how much smaller, how much bigger, the change, it's a subtraction. So how much smaller is it? Well, one's 9, the other is 6, the difference is 3. This guy is 3 inches smaller than that guy. So how much smaller is the smaller side than the bigger side? The smaller side is 3 inches smaller than the bigger side. And I guess we could even say You could even throw in, if you wanted to, a little more detail. The smaller side, which is 6 inches, is 3 inches smaller than the bigger side, which is 9 inches. A little extra detail never hurts an answer. You do not want vague general answers. You want your answers to be specific, clear. Put in as many numbers as you want. Be specific in your answers. Don't just say, I found the volume of each of them and the side length of A is bigger. No. Say, I found the volume formula, I took the square root of each side, I found the side length of cube A is 6 inches, then for square B, I used the area formula, I square rooted each side, I found the side length is 9 inches, therefore the cube has the smallest side length. And then for the second part of the problem, the smaller side, which is 6 inches, is 3 inches smaller than the bigger side, which is 9 inches. The more detail you have, the better your answer will be. If you could please go ahead and answer this question in the summary box of your note sheet. It says, how can square/cube roots, so square roots or cube roots, be used to solve equations? That should be easy to answer because we did it the entire class period, but go ahead, pause the video, do it right now, and when you're ready to continue, hit play, and we'll go through it together. So I have here, square roots are used to undo the squaring of a variable. This helps to get the variable by itself. So if you have a variable squared, you take the square root of it to get the variable by itself. And the same thing is true for cube roots undoing the cubing of a variable. So if you have a variable cubed, if you take the cube root of it, it gets the variable by itself. It's not being cubed anymore. So that's how they can be used to help solve equations. This has been lesson 1.4. Thank you for watching.